All right, guys, good morning. We are going to continue with the lecture from last time. Last time I introduced AC, alternating current, alternating voltage, and we talked about a couple terms. We talked about amplitude, we talked about period, we talked about frequency, as well as some other things. These are the big three. These are important concepts. What I want to do, I want to review this quickly, and then I want to talk about some important AC values for current and for voltage. So just to review, we know that a DC waveform over time, if this is voltage or current, over time is pretty boring. It looks like that, or this. And what this indicates is that for DC, regular DC like from a battery or power supply, the value of the voltage doesn't change over time. The value or direction of the current does not change over time for DC. If I were to draw the same type of graphs for AC, I have to draw them like this. AC, let's say current, I would draw like this. What this indicates is, this is time, say from t equals 0 to whatever this time is right here. The current is doing two things. It's going from 0 to some maximum value. Here's the max value of the current. This is the amplitude. So the height there is the amplitude. So it's going from 0 to some max value back to 0. But for this whole portion, remember this whole thing here is called a cycle. That's one cycle. For this half cycle, that means the current is going in one direction. So for example, you know that when you plug something into the wall outlet at your house, the plug has two blades on it. And it goes into whatever device you have. And I know it's a glare up there, so hopefully you can still see this. What this means is, if this is AC, then the current is actually going into one of these terminals, going through the device and coming back out from this point to that point, and it's also going from a magnitude of 0 to some maximum magnitude back to 0 again. And then for this part of it, this process has reversed. We start at 0 and we start to grow again, but notice it's in a negative direction. This is a negative current. The meaning of a negative current is the direction has changed. So instead of going this way and out, now it comes back this way, and this alternates back and forth as these cycles repeat. The amplitude will be the highest or lowest point for a cycle. And we defined, last class, we defined the period to be the time for one cycle. So if this is t here, the period would be from this point to that point, and I use this funny looking t to represent the period. And the period is given in seconds. So it might be so many seconds, or more likely milliseconds, or microseconds, or even picoseconds. So the amplitude, we said that was the highest or the lowest point of a cycle. The period is the time for one cycle. And the way to think about frequency is, if you actually think of this as a wave that's moving down, imagine if you took a rope and you tied it to the end of the wall. If you did the rope like this, what you would see is this waveform. And if you can see how many of these cycles move past a certain point in 1 second, that's frequency, the number of cycles per second, the number of cycles that exist in the time space of 1 second. We said that amplitude, the unit for amplitude, well, depends on what variable we have here. If I have an I here, then the amplitude would be in amps or milliamps or some form of it. But I can also switch that I out and put a V here. So I can look at current over time or voltage over time. If I put a V there, Then the amplitude is the highest voltage. The period would be the time, again, for one cycle, and the frequency, the same as the definition from before. The difference is if I put when I have an I here, that means the current is changing direction. If I put a V here, what that means is for the first half cycle, the polarity, using the same example, the polarity might be like this. And then for the second half cycle, these reverse. And the polarity actually alternates back and forth according to this graph down here. So alternating current, alternating voltage. And again, the unit for frequency, we said that is the hertz. You might have seen that unit before. We'll just use a capital HZ for it. But it's named after a person, Hertz, so I'm going to spell it out. So you might have something that's 1500 hertz or 1.5 kilohertz. So you've probably seen this unit before if you deal with anything electrical or computers or anything like that. You've seen the hertz before. And then the only other thing would be relationships between the two. Frequency is 1 over period, and period is 1 over frequency. So those are the equations I gave you to remember. And then there was the one for just the AC waveform in general. I wrote it this way when we first start talking about the graph. But we'll come back to this a little bit later, either today or next time we get together. What I want to do today, though, is talk about some important AC values, and I want to define one and make sure you understand the important one that we're going to use most of the time for our calculation. So let me list them. I think I ended the last video with these values, so I'm going to start this video with the same thing. So here are the list of the important AC values that I expect you to know. And I'm going to give the symbols for these two. I'll write them out first. So it's the instantaneous value. There's the peak value. There's the peak-to-peak value. There is the average value. And then there's the RMS value. This is also called the effective value. So in your notes, these two right here are actually the same. Just different names for the same thing. So I'm going to get rid of these and just write down the symbols. You go ahead and write this down in your notes so you have them. I'm only going to work with the symbols so that you know what they mean. And the one I want to talk about is the RMS value. That's pretty important. So I want to actually take some time and go through and explain exactly what we mean when we say RMS. What is that a measure of? So let me get rid of these. So what I'm going to use are these symbols. A lowercase v, that's the instantaneous value. For the peak value, it'll be a capital V, subscript P, and then the peak-to-peak value, the same thing with two P's. So peak-to-peak will show this way, average. Sometimes I'll use an E, sometimes I'll use a G. And then RMS is this. And just remember, VRMS is the same as, this is the effective value. So again, there's two names for the same thing. They're exactly the same. I'll use both of those names. So there's my list of important AC values. Now, whatever I say for voltage also goes for current. So if I wanted to, I can show an instantaneous current by using I use a script I like that. I can show a peak current like this or a peak-to-peak current like that. Whatever, all I gotta do is exchange the V for I, and I got the same equivalent for current. Now, how do I get these values? How do I calculate them? Well, this first one is for the equation I gave you last class. That for AC, V, the instantaneous value is VP sine theta, where P is the peak value. Theta is the angle that the generator makes in the magnetic field that we talked about as it spins around, and V is the instantaneous value. I'm going to talk about this, but I won't really. We might do one or two calculations with this, but what's important are actually the ones below it. And again, the most important one is the one down here, the RMS value. But just as an example, if I say that V equals 50 sine theta, if you want to give me the value for voltage at a certain degrees, then what you do is you just put this in your calculator. You might have 50 sine 40, or let's say 73 degrees. And you would put that in your calculator, make sure your calculator is on degrees. You put it in your calculator and you get a value for V. That would be the voltage at that particular angle, the instantaneous voltage at that particular angle or time. Now, usually I don't answer this. I mean, we only talk about this so you can kind of understand what AC is. But the values that we'll deal with more are the ones below it. And again, the average, the RMS value is what's important. But notice the way this was written, if I clean this back up, the way this was written was that script V, the instantaneous voltage, was 50 sine theta. Since we know that AC is VP sine theta, that means that 50 is the peak value. This is the peak value. So what I can do is I can give you a problem written like this and ask you to calculate these. Given that you start, you know that that's your peak value. So 50 would be my peak value. You get that just by looking at the problem. So given it in this expression, 50 would be my peak value. And then what I wanted to give you were the equations to get the rest of the variables here. So peak to peak, let me show you when you measure peak to peak. For this waveform, my amplitude would be 50 volts. 50 volts is the peak value. Well, that means I got 50 up this way, and over here it goes down 50. So over here, I got negative 50. Because I got a positive peak and I got a negative peak. So this peak's at positive 50, this peak's at negative 50. Well, the peak-to-peak value is when I measure from one peak to the other peak. So I got 50 here. You just ignore the negative sign. I got 50 here and 50 there. That means from here to here is 100. So in other words, my peak-to-peak value is just 2 times the peak value. So for this waveform, I can write the peak value is 50 volts and the peak-to-peak value is 100 volts. You can show it either way, it doesn't matter. Now, if you're wondering why do we have a peak value and peak-to-peak value, well, if you were in class, if you think about back to the lab, we had a big piece of equipment in there that we never got a chance to talk about. It had a screen on it, and on the screen was a grid. Well, that's called an oscilloscope, and that's what you use to measure AC waveforms. You would actually see this waveform on that screen. I'm assuming that when you guys do your labs, you're using Multisim to do labs. But I'm sure Russ will have you do something with there's a built-in oscilloscope in Multisim, and you'll see this. But I think you guys are probably still doing your DC stuff. When you get the AC, you'll actually do this. You'll see it. You'll see the waveform. You see that you can measure. You can't measure frequency directly. Multisim may tell you, but in the actual lab, if you had the analog oscilloscope, you would measure the period, and then you would use that formula I gave you earlier to convert the period to the frequency. So you'll see this when you get to this in lab. All right. So again, given this expression, you get the peak value by just looking right there. Peak to peak value is twice the peak value. So if I double that, I get 100. And then the average value, let's talk about that. The average value. Let me give you the equation for average value just so you have it. To get the average value of an AC waveform is 0.637 times the peak value. 0.637 times the peak value. Now, if you think about what do we mean by average? So if I want to find the average, oh, by the way, speaking about average as your exam, I'll post your exam grades here, I guess after the lecture. I didn't get a chance to do any posting of grades, but I'll post them right after I get done here and you can see what you got for your exam. But so if I want to find the average of your exam, how would I find that for your exam? What I would do is I add up all the scores and I divide by the number of people that took the test. That gives me an average or middle score. Well, you do the same thing here. If I want to find the average of a waveform, I do exactly the same thing. So I might take a waveform like this. Now remember that keeps repeating. Let's just say it's voltage. It could be voltage or current. So what I would do if I want to find the average, I take values from this side. I take these values. So this value right here would be right there. This value right here would be right there. This value would be right here. I get these values, and now I add them up. But we got a problem. If you think about the way a sine wave is, if I use a whole cycle, for every positive value over here, let's say I choose this value, whatever that value is, for every positive value over here, I got a negative value over here. And if I add the positive values and the negative values, I'm going to get a 0. The average of a complete cycle of a sine wave is 0. So that's kind of useless if I take the average of a whole sine wave. So when we do the average using this equation, that's always the half cycle average. It's not the average of a full sine wave. It's the average of half cycle from 0 to 180. And that gives me the average value. Now, the average value, if I take the peak value, which is this, let's just say the peak value was 100. That was 100 volts. And VP is 100 volts. Then the average of this, from here to here, the average, using this equation, the average would be 0.637 times 100 volts, or would be 63.7 volts. So the average is like this, 63.7 volts. Now, that actually is not important for what you're going to do in this class, but if you took other courses, then you can actually make use of that. That comes into play when you're, I think I mentioned to you earlier when we talked about AC and DC, the difference between the two. Well, I don't know if I mentioned it or not, but you have DC, you have AC. AC is really, really important when you want to move energy from one place to another. You can move energy in the form of DC. You can move energy in the form of AC. The problem is if I move energy, electrical energy is what I mean. If I move electrical energy in the form of DC, it's very, very, very inefficient. Now, I don't have time to go into the reasons why. Maybe I don't know if you guys are going to do a transformer lab. There's a device called a transformer that allows you to take AC voltages and currents and make them bigger or smaller. And it turns out that using that device, making the voltage really, really, really big when you want to transmit it from point A to point B across, let's say, the country or the city or something, is way more efficient to move the energy in the form of AC than it is DC. We move the power at a high voltage, low current. When we get the power we want it, we reduce the voltage back down to bring the current back up. We got Nikola Tesla to thank for that. But again, if you're interested in that, send me a link or send me a text, and I can point you to some videos that'll explain that. But we have AC mainly because we want to transfer energy from one place to another. But when we get the energy where we need it to be, normally we convert that power back to DC because it's easier to design machines that run by DC than by AC as a rule of thumb. That's not always the case. So anyway, that's the peak-to-peak value. That was the average value we just did. Now, the one that's really important though is the RMS value. The RMS value. So the same example, let me use the same example because the numbers are easy. If I gave you V equals 100 sine of the angle, if I gave you that, and I asked you to find the RMS value. Well, it's easy to do. The RMS is, I didn't give you the equation for it, is 0.707 times the peak value. And by the way, these numbers is 0.637 and the 0.707. If you wonder where that came from, if any of you taken calculus before, you can actually through calculus and something called integration, you can actually get these numbers right here. You can go through and do the math that show you where these numbers come from. We don't worry about that in what we're doing. We just use them. But if you wonder where they came from, you can actually go through. If you know calculus, you can go through and you can get these numbers to see where they came from. But again, we just want to use them. So RMS would be 0.707 times, this is the peak value, 100 volts. So the RMS value here for this waveform would be 70.7 volts. That's also the effective value. VFF is the effective value, is 70.7 volts. So what I want to do today, probably the rest of the time, is what do we mean? We say we have an RMS value of 70.7 volts or an effective value of 70.7 volts. Well, RMS, let me write out what that means. It stands for root mean square. It's either square or squared. RMS, root means square or root means squared. It's probably the correct way to say it. And what this is, if you took statistics, if you ever had a statistics course, you'll see that's a special kind of an average. And there's a square root in it. The mean is a special kind of an average. And the square is just what you do when you take a number and you raise it to the second power. They actually name this value after the mathematical operations that you do to get the answer. The root means squared. So that's the technical definition of it. But what does it really mean? What is an RMS value of 70.7 volts? What does that tell us? That's what I want to talk about and make sure you understand. And I'm spending time with this. I could just give you the equation. We can go on with this, but I think this is pretty important to understand what it is you're getting when you get that number. And the way I'm going to help you to understand it is by doing a little experiment on the board, a thought experiment. We'll think about how this will work. So imagine I have a circuit that consists of a battery, a DC battery. A 100-volt battery. I have a switch. I have some water right here. I have some water in a pan of water. What I'm going to do over here is, in the water, I'm going to put a resistor. You got a resistor we hook up to this wire. like this. So it's a pretty simple circuit. I got a switch. I got a power source of 100 volts. I got a resistor. I stick the resistor on I connect wires up to it and stick it in some water. When I close the switch, current's going to flow in the circuit. That resistor is going to heat up, and that's going to heat the water up. So what I want to do is I want to measure the temperature. So I'm going to stick a thermometer in the water. I stick a thermometer in the water. The switch is open. If I put a thermometer in the water, with the switch being open, basically all I'm doing is measuring the temperature of the water. So I just let this sit here in the water, and I figure out what the temperature of the water is. So let's say the temperature of the water is right here. We'll call it T1. I close the switch. Now current flows in the circuit. That resistor is going to heat up. The thermometer is going to raise up, get a higher temperature. So let's say it raises up to right there. We'll call that T2. Now I'm timing this. I got a stopwatch. I hit my stopwatch. I let this heat for a certain amount of time. I stop the stopwatch. I see how long it took for the temperature to go from here to here. So here's my starting temperature. Here's the temperature where I'm going to stop. When I stop, I open this back up. And what should happen when I open it back up? The water is going to cool back down, and we'll assume that nothing changed. It's going to cool down to exactly where it was before I closed the switch. So it's going to go back down to T1. Now, if you think about what I just did, it's kind of slick the way this works, because we've converted basically the energy with the power dissipation, how much heat we're getting rid of per unit time. We've converted that to a temperature. So now I have something to compare to. What I want to do is get rid of this battery. I'm going to take the battery out and move it aside. Let's just set it up here for right now. So my battery is sitting there. And remember, this is DC. Well, what I'm going to do is get an AC source. I don't know if I drew an AC source before, but this is an AC voltage source. Here's a DC voltage source. AC, DC. So what I'm going to do is remove the battery and put an AC source in here. That could be a generator. That could be coming from the wall outlet. It's something that will give me an AC waveform. Now what I'm going to do with the AC waveform is put this arrow through it like this. What does an arrow mean when you have it through a device like that? Like if I show you a battery of 100 volts, that means I get 100 volts out of that battery all the time. But if I draw an arrow through it like this, that means it's variable. In other words, there's a knob. I can change this probably from 0 to 100. So now I can do a range. This goes from 0 to 100 volts. It works the same way. You guys saw you saw a resistor. Here's a fixed value of resistance. If I show you the arrow through it like that, well, that means I can change the resistance. I can vary it. Or you may see it like that. That's a potentiometer. That's a rheostat, or variable resistor. So an arrow through a device means I can change it. So I'm going to put an AC voltage source here, 100 volts, but I got an arrow through it, which means there's a knob on this thing. I can turn it from 0 up to 100. What I'm going to do, though, is I'm going to start this off at 0 volts. So before, see if I can draw a graph. Before, when I had the DC source, I draw a graph of it. I had the DC source in there. So I had 100 volts DC, And this is time. What I did, I closed the switch with the battery in there. So I was putting energy in the form of DC into the resistor, heated up the water and gave me a temperature of so many degrees Fahrenheit. Then I opened it back up, so then it cooled back down like that. I want to do the same thing, but I want to figure out how much AC, where do I adjust the knob on the AC power supply to raise this temperature up to exactly the same place where it was when I had the battery in there. So what I'm saying is, AC looks different than DC. DC looks like this, it's flat, but AC, I put the same amount of voltage in, 100 volts, but it's going like that. It's a wave. And I only get power during that part, or that part, or that part, or this part of the cycle. I don't get anything like, well, that's zero, or that's zero. Matter of fact, if you compare these, let me make this a little neater, because this is actually kind of important. If this is my DC, this is my DC. See if you can follow this. Let's say my DC, I have a really nice DC pulse. There's time, there's volts. It was 100 volts DC. So what I did, when I had the battery here, I got DC, which means I had no variation. And then when I turned the power, when I opened up the switch, the voltage basically was stopped. In AC, what I have is I got a wave. So really how I draw the wave, if I draw it like this, or if I draw it like that, that's going to depend on the period. Remember, the period is the time for one cycle. This period is shorter than that period. So one cycle is this wide in time, or this wide in time. This has a shorter period or a higher frequency. This has a longer period or a lower frequency. So what if I had this so that I had just one, I opened that switch at right about where there's 1/2 cycle of the AC waveform. In other words, the AC goes like this. It continues to go. What if I open up this switch right here for the period of that AC waveform? This peak value, let's say I turn this up to 100 volts. Because I'm thinking, when I had the 100 volt DC battery in there, I got this up to T2. Why don't I just turn this up to 100? And I want to show you that that won't work, because 100 volts for DC gave me this. Well, 100 volts for a half cycle AC, going to peak up to 100 and go down, and it's going to keep going to give me the full cycle. But what I want to show you, if I only looked at half a cycle, if I make that half cycle equal to the time where I open the switch, then you can clearly see that the AC is providing power only for this part. The DC was providing power for this part, and for this part, and for this part. For that whole time T, this T, for that whole time, the DC was providing power to that resistor. So it's going to move it up to T2. But for AC, it'll never get up to T2 because I'm only providing power for the part that's under the curve. What I want to do is I want the AC source and the DC source to provide the same amount of power or heat to the resistor. So what I'm going to have to do is turn this up a little higher than 100. I actually have to make this AC come up a little higher, because what I want to do is push it down. So when I push it down, what I'm after is this. I got this square, this box that represents the DC. Well, what I want to do is take the AC, push it down, and when I push it down, you can imagine it's like a piece of rubber. When I push it down, when the DC and the AC lay right on top of each other, like that. I keep turning this up, pushing it down, turning it up, pushing it down, until I can get the green part of it to, when I press it down, to fill out or just kind of trace over the black part. When that happens, I know the AC and DC are doing exactly the same amount of work. And hopefully you can see from this graph right here, Now, if I want to smash that green part down and make it cover the same area as the black rectangle, I got to turn it up so it's a little higher. I got to have a higher peak voltage to give me the same amount of electrical work or the same temperature as the DC, the black voltage up there. So it takes more AC to give me the same amount of heat as the DC. So I keep turning this up. The peak gets higher. I push it down to see if it covers that area. Turn it up higher. Eventually I'll get to the point where I get the peak that when I smash it down, it'll cover that same exact area. And when I do that, what will happen is the thermometer is going to go up to exactly the same point. This was from the DC, the temperature from the DC, and this is the temperature from the AC. I just keep turning this up. It won't be 100, it'll be higher than 100 because it takes more DC, it takes more AC to do the same amount of work as the DC. But when these two temperatures match, what I can say is the heating effect of the DC and the heating effect of the AC are exactly the same. In other words, I'm doing the same amount of electrical work with the AC source and the DC source when these two temperatures match. When the temperature from the DC source matches the temperature from the AC source. What I'm trying to show you from the graph, it's going to take more AC voltage to do that. It's going to take more AC to give me the same amount of heat as that DC battery. That's what RMS is. So what am I talking about? Well, let me give you a mathematical example. If I gave you this problem, if I gave you the problem that we had before, if I gave you a peak value, let's say I gave you a peak value of 100 volts, and I asked you to convert that to RMS. Well, that's easy to do. You use the equation. You say VRMS is equal to 0.707 times the peak value. Peak value is 100. That's going to give me 70.7 volts. So 100 volts peak is equal to 70.70 volts RMS. If I apply this idea to that, what I'm saying is a 100 volt peak AC signal is doing the same amount of work as a 70.7 volt DC battery. I'll say that a second time. A 100 volt peak AC signal is doing the same amount of electrical work. What I mean by that, it has the same heating effect. So it's doing the same amount of electrical work as a 70.7 volt battery. So now you know the meaning of effective value. Effectively, this is when we say effectively is doing the same amount of work as a 70.7 volt battery. So they call that the effective value. V effective would be 70.7 volts. So effectively, this 100 volt peak is doing the same amount of work as a DC battery that's 70.7 volts. So hopefully that is clear. If not, you might have to rewatch this video. You don't have to know any of this to do the problem. All you got to know is the equation. Anybody can stick a number in there. I'm trying to give you an idea of what we mean. You kind of give you an intuitive feeling. What do we mean when we say RMS? And it turns out that I'm harping on this. This is really important because when we do a calculation in AC, you got all those values I had before. We have the instantaneous value, we have the peak value, the peak to peak, on and on and on, right? Well, it turns out that the one that's most important is the RMS, or the effective value. Usually when you do a problem, at least for me, you assume that the value is RMS unless I tell you something otherwise. So when you get a device, you go buy a device from the store and it plugs into the wall and it says 100, you'll see 120 VAC, 120 volts AC. Well, what voltage are they giving you? Are they giving you the instantaneous voltage? Are they giving you the peak voltage? Are they giving you the peak to peak or the average? Which one are they giving you? They're giving you the RMS value. They always give you the RMS value. So that's what's important because they're relating the RMS, they're relating DC to AC, AC to DC, and vice versa. So for us in here, the RMS value is very, very, very important. Now, what I'm going to do is give you some problems. I bought a new printer. Actually, I had it, but I hooked it up. And I was able to scan your exam and scan, but then the thing stopped working. So I'm going to try to get that working. I'm going to give you some problems where I give you, say I give you the RMS value and I want you to find the peak, that kind of thing. Or I'll give you one, you got to find the other value. I'll give you some of those where you practice doing frequency, calculation, period, that kind of stuff. And then we'll get into some circuits. So I think that's all I'm going to show you. I know this is a lot. Like I said, you don't have to know any of this to do the problem, but it helps to understand what RMS is to get a really, really good understanding of AC and how it compares to DC and all of that stuff. So I think that's all I want to show you for today. I've used up a whole lot of time explaining stuff today. Does anybody have any questions for me before we sign off for this session? And I even asked you guys if you can hear me. I hope you can hear and see me and all of that. Can you see me? Okay, well, Rusty, you have a question?
Yeah, I was just wanting to clarify that the test 2 is due next Monday.
Yep. I figured I'd give you extra time. Normally, when there's a take-home test, I give you time to think about it. So it's next Monday. We'll see how that goes. Try to get it in. Try to get it done before then. But next Monday, the link will disappear, and you won't be able to upload it.
Okay.
And then we got a total, because we're really supposed to have 4 tests, guys. So because of the way the thing happened, I tried to spread it out. But some kind of way, I got to get 2 more tests in there. So we'll see how that works out. I'll work it out. Don't worry about it. I'll post your exam grades here in just a little bit, so you can look for those. And if you have any questions, I'll leave it next session. I'll leave some time open where we can go over those exams. Oh, wait a minute. I think that's a retake, so you don't have to worry about it. But the one that you're doing now, we'll leave some time open. We can look at those problems if we have to. So yeah, the 13th, I think, is a due date. And so don't miss that time because on the 13th, the link will disappear and you won't be able to upload it. Anybody else have any questions? Okay, then. Well, you guys have a great rest of the day. Stay safe, and I will see you same time on Wednesday.